Hello and welcome to this linked live interview brought to you by the Human Brain Project. My name is Jörg Conradt and I'm an associate professor in the Division of Computational Science and Technology at the Royal Institute of Technology in Stockholm, Sweden, KTH. Today I'm having a chat with Yannick Morel from the Cognitive Neuroscience Department at the University of Maastricht in the Netherlands about some of the work that we are doing together. Specifically, today we'll talk about work that we are doing in the Human Brain Project on what people call Cobotics. I would now like to welcome him to join me on screen. Yannick, please join.
Hi, Jörg. How are you doing?
Hello, Yannick. Good to see you. I'm fine. How about yourself?
I'm doing very well. Thank you. Thank you very much.
So, Yannick, I mentioned Cobotics. What is Cobotics?
Okay, so it's a short form for collaborative robotics, which describes the notion of having or trying to have both a robot or robots and a human working together on the same task at the same time. And the reason people have been looking into that are like trying to see whether they could make it happen. Some of the motivation there is that you have different sort of respective set of qualities to like both sides of that equation, right? So you expect the human to be in some way smarter, right? So like context awareness, critical thinking, that type of things. And then the robot itself brings different qualities. It's a machine, right? So like it's more accurate, it's precise, it's repeatable, and also you can set it up that it can carry like heavy payload, right? So the notion is that there's a lot of tasks in industry that people have been looking at and thinking that, well, you know, it would be cool if we could bring to bear those different set of qualities on that task. And the notion is that you would be able to solve those tasks better, or like to be more productive, or to just do better at the task specifically.
So that sounds super exciting. And you've mentioned that's good for industry, for factories. I really don't see many of these robots in factories today working together with humans. So why is cobotics not widely used in factories?
So yeah, I mean, you're right, and I think it's even the opposite, right? I think if you go to a factory floor today, you will see setups where people go out of the way to try to enforce the opposite, not human and robot working together, but like clear separation between human and robot. And the reason why people are doing that, the reason why we, instead of like having human and robot working together, they're separated, is simply out of concerns for safety. So if you think in terms of how you want to operate a robot next to a human, right, you want to make sure that the way that the robot is moving is not going to be threatening, or it's not going to be dangerous for the human, right? Because you don't want collision, you don't want the worker to be hurt. You need to be able to ensure safety. What you necessarily need to be able to achieve that, you need to have the technology on site so that you're able to figure out where the human is going to be in space next to the robot, right? You need to know where the human is so that you avoid for the robot to collide with the human. And the reality of the technology that is being used in industry right now, the type of stuff that you see in factories, is that we're not able to guarantee that, right? If you try to figure out where the human is going to be in the scene, you're able to do a very decent job, but you're not able to bring any thought of guarantees of knowing exactly where it's going to be, right? And if you don't have guarantees of like knowing where the human is going to be, you don't have guarantees of safety, and so therefore you cannot have human and robots next to each other.
Okay, I understand that problem, but that's a pretty big problem, and it seems there are many different aspects that need to be addressed to enable such cobots in factories. Which aspects do you work on?
So we look at different things. Yeah, we have, and it's not just, of course, like the both of us, but we have like a good number of colleagues that are working together with us on some of the different aspects. And that safety issue that's connected to perception problems or lack of robustness in perception That's of course some things that we want to look at very carefully, and some things that we'd like to bring new solutions to try to solve that. But we don't like limit ourselves to that. We also look beyond that, yeah, assuming that we're able to clear that obstacle. What are the type of things, you know, in a world where you have like human and robot working together, very close to one another, sometimes in contact? What are the things that you would want to pay attention to? Or like what are the things that become like very important that you did not have to worry about before? For instance, if you think of a robotic arm and a human interacting, exchanging objects or manipulating objects together, all of a sudden you want to pay attention to the planning of the movements of the robots, right? Because they're in proximity of each other. There, if you will, the robot is in the safety space or like the personal space even of the worker, and there's work that you can do there to plan the movements of the robot in such a way that you make the worker more comfortable and develop a better sense of trust from the human towards the robot. You know, another thing that we're looking into, taking it like one step further, if you think of situations where they're working together, for instance, on some sort of like collaborative assembly, right? So they're trying to move a piece and put it on some sort of assembly. Is there manipulating the same objects together? You're going to have some exchanges of efforts between robot and human. And you want to look into how you control the movements of the robot so that you're both able to achieve the task that you want to do. But at the same time, you want to be mindful of how this is going to affect the movement and the, if you will, the musculoskeletal system of the human. So you don't want to apply like unnecessary or like dangerous stress on the human frame, so to speak.
Isn't that solved by robot companies these days? I mean, people sell robots that are supposed to work with and close to humans. So what are the exact research points that you look into how to improve such?
So that's on the external effort. So that's a good point. And people do that, for instance, for like exoskeletons, right? Where they need to address that specifically. But typically the way that they do it, it's a balance between, if you will, like passive and active. So you have passively compliant joints on the different points of actuations, so that, if you will, the human has some wiggle room. It can move around without like hitting the limits of the robot. And then you have like an active component to that, right? Where the robot tries to be aware or cognizant of what is the human configuration and what is acceptable and not acceptable in terms of the movement from the robot, in terms of the impact that this is going to have onto the human frame. And we're looking at that, but we try to take it like one step further. And before I want to take a step further on that, let me take a step back. We work on those problems. You, I, our colleagues within the HBP, we come mostly from engineering, right? Us being in the HBP, part of the motivation, or like part of the reason I was excited to come into the project, is because it brings us like some special opportunities. So specifically, we're here and we're able to work on those cool problems. A lot of them, you know, have not been resolved well. So a lot of them are either open problems or problems for which there's a lot of room to improve solutions that exist out there. So there's a lot of room for contribution, but also typically those problems also have been solved, or like for some of them have been solved by the human brain very well, right? And what's cool and exciting about the HBP is that we have colleagues that are in neuroscience and that are investigating how the brain is solving those problems. So they develop models, they have assumptions, hypotheses, and insights into how this is being solved. And what we're able to do, like what we've been able to do on my side of this topic, is partner up and join up with those people looking at those problems and how they're being solved by the brain, looking at that from the neuroscientific perspective. And then we look at what are their insights in terms of how the brain solves it, and then we try to emulate that and replicate those models and try to apply that on technological applications. Then going back to what I was saying about modeling of human movement, what we're able to do, because we're working directly with people that develop model descriptive of how we're moving, right? So we're looking at exchanges of efforts, for instance, between a human arm and a robotic arm. We have not just the physics of the human arm included, so the musculoskeletal model, right? And we can monitor stress and tendons and that type of things. We're also working with the people that describe the neural circuitry that then controls the musculoskeletal model. So we go up in abstraction, and we're not just describing the physics of the human, in terms that the robot then can become aware of the stress applied and so on. We can go up and describe, for instance, like what are the reflexes of the human, right? If there's an unexpected movement that's imposed on the human arm by the robot, how is the human gonna react to that through its own like reflex, right? So we can anticipate a lot better what's going to happen, and integrating that within the artificial agent, within the robot brain, if you will. Then the robot becomes a lot smarter and a lot better able to anticipate what the human is going to be doing.
So you're saying it's safer for the human, not only when everything goes smoothly, but also when there's some misconfiguration or some unexpected event happening, that you can react better. Is that correct?
Yeah, exactly. So you not only the model doesn't just describe like the reality of like what's happening right now, but because we know we have some description of how the human would react, we also, if you will, like are able to predict the future a little bit, right? Like based on what's happening, based on intentions, based on how human reactions work, as per the neural circuitry controlling it. We're able to account for that and anticipate issues. And then when something unexpected happens, as you were just saying, when we go off script, we have a much better idea of what's going to happen, and we can use that to try to mitigate the issues.
Very well. Now we heard a lot about your research, and maybe if there's time, we can open up some more of these boxes. What I'm curious about is, now that you're saying what you're doing, how ready to use is that? Is that picked up by industry? Are they implementing this? Is this visible tomorrow?
So no, not really. This is we're working at a fairly fundamental level. So as mentioned earlier, we're trying to develop new solutions for problems that have not been solved well by engineering, essentially. And we're trying to look at how the brain does it, and we try to leverage those insights to try to develop like new stuff. So it's very fundamental work, and this is not. We're developing, if you will, like proof of concepts and prototypes that remains essentially academic work. So if you think in terms of like technology readiness level, I don't know if you speak TRL fluently, we're like up to TRL 3 to 4 maximum. Whereas in industry, you need to go much higher than that. But the point is that this is still very so it's very exciting work, it's very interesting work, and also before the industry is able to use it, you need to lay the foundations, and this is what we're doing now. We are laying those foundations, and we are on our way to transcribe that down the line with into results and products that industrial partners are going to be able to use.
Can you talk a bit more about the day-to-day work for yourself and for your PhD students? So are they working with pen and paper or computer simulations or physical systems, or do they interact with robots?
So we work mostly in simulations. So we work, both pen and paper, simulation, digital modeling. When we need to, so we try to be grounded in physics, right? So we're looking at the reality of how the humans are moving. We have dynamical models for that. We simulate that on computers. We also have the physics of the robots. And then when we invent new things, so because those physics are well described in the literature, well established, and it's not rocket science. It can be complicated, but it's done work, yeah. But when we do new things, for instance, when we come up with, let's say, like new sensing modalities or like that rely on physics that are not well described, Then we put in the work to go back to the physical world, taking the measures, and then characterize the physics of what we're playing with to be able to describe it, if not exactly, at least faithfully enough in simulation that the simulation is making sense, right? But so to go back to what you were saying, yeah, we work then on computers in simulation. Those computers, they're a good, if you will, it's a meeting point of a common ground also for the people who work with that are working on neuroscience. The people we work with, so they work on some of those problems being solved by the brain, some of those functions supported by the brain, and they do that using neural network models, right? So they themselves have what they call like a neural simulation, where they have a mathematical model describing how they assume, believe, hypothesize that the brain is working. And they run that simulation on a computer, and then they look at the input-output and try to infer some insights from that. And so those models, they're, if you will, like the point of connection between them and us. We're able to, not directly take those models and like plug them in our own simulation, but it's a starting point, and this is a place where we meet essentially.
Along the discussion, you've also mentioned motor control. So these robots have to move and have to decide what and when to do. What is exciting about motor control? What do you work on in there?
So on motor, so the work that we do on motor control actually is what I was referring to earlier. We're looking more closely. We're doing more modeling effort on the motor control of the human limb, right? To anticipate like movements and be able to control the movement of the robot specifically. On the robot itself, we're not doing anything special. We're doing just like baseline control theory, which is actually my background. Baseline control theory result to control their movement. But it's interesting because we're doing then a lot of work on modeling of human movements and control, and this is something that also becomes interesting to the people that are working on neuroscience on the same problem, right? Because we're interested in having a faithful model of how the humans move, for the reasons discussed before, being able to describe the reflexes, being able to anticipate what are going to be the reactions. Then conversely, the people working on modeling from neuroscience perspective of if you will, sensory motor loops, so description of the neural circuitry that support those functions, they have a pretty solid understanding of how it works, but there's still a lot of question marks in terms of like how specifically, what makes it tick, how things are coming together, the nature of certain signals like along the way. So they have a lot of questions, and working together with us, essentially we're looking at the same substance or the same problem, the control, for instance, of like some persons like upper limb. And we're looking at that from like different perspectives. There are very detailed neural models of different brain regions that become involved in the motor control problem. And in the meantime, we work very often with abstraction, functional abstraction of those same brain regions. And looking at the same problem from different perspectives, talking with them, we learn how to do the control a bit better or different or like more faithful. And then working with us, they also understand the shortcomings in terms of performance, for instance, of what they're doing. Performance compared like to how humans actually like perform. So we're able to help them advance through, grounding really what they do in a fairly faithful description of the dynamics, of the resulting dynamics of the system. And conversely, we're able to get a lot of insights from what themselves they are doing. But okay, that was a lot on the type of thing that I'm interested in and I'm excited about and that I work on. But so, as we just said, so my work, or like the work we do, is mostly in simulation. You, on the other hand, you do the real thing, right? You're like a challenge. You work with like real world, like physical robots. And also you work specifically with brain-inspired sensing and computation, right? If I understand that correctly. So can you explain to us? Yeah, go ahead. What
Sure,
is that? And why
So
is
that's
it so
all correct.
exciting?
I don't know, you phrase it the real thing. Now let's look at this from a different angle. You and me, we're both engineers. We come into this field, into this human brain project with a different mindset to many other people in the human brain project. We have some idea of how traditional control handles machines, handles robots, handles any system that we have. You can write some equations, and then the control computer will maintain a stable point of operation. Now that's in a way similar and in a way also very different to how the brain works. I mean, the brain does follow some equations, we believe, but it's a vastly different distributed system. It has all these different neurons, all these individual neurons. In a way, the brain has the very same duties, the very same functions that we want our controllers to be, which is get some sensory input, understand what is going on around it, and produce some motor output. Yet it does that. It finds solution very, very differently compared to our traditional engineered controllers in control theory. So a large part of what we in my group do, my students and I do, is about understanding how to use benefits from such brain-like computation and apply that to technical systems. So in a way, we collaborate, we talk a lot with neuroscientists, with computational modelers, with people who simulate the brain or parts of the brain. We try to understand how these simulations work, but not preliminary to improve the simulations or to better understand how brains work. That's not our main goal. Our main goal is to understand the benefits of such different computation and apply those to technology. So we have a lot of robots, we have a lot of technical systems in the lab. I can probably mention a few of them later. And the commonality among those robots is that we try to use brain-inspired algorithms. That can be neural networks, but it can be other brain-inspired technology that produces motor behavior, motor output of these systems. So a typical example is event-based processing. In the brain, we don't have continuous equations. We don't have a line of mathematics that performs some action, but instead we have neurons. And the way these neurons communicate with each other is through spikes, through pulses, discrete pulses. So every once in a while, a neuron sends out a pulse, an event, to other neurons. And only when another neuron receives such a pulse, it can process that pulse, it can process new information and update its internal state. So this is a term that we can call event-based processing in a computer science context. So we develop processing systems, computer systems that use such event-based information handling. We have sensors that produce spikes, that produce events instead of continuous values. We have computers that can operate on those spikes and only compute whenever there's a new spike coming in.
So I really like some of the things that you said. Like I couldn't agree more in terms of like the parallel you were drawing, you know, in terms of like the input-output perspective. Yeah, like so the sensor perceiving like what is the world is what is happening in the world. Then you have actuators that are acting on the world, and then you have the intelligence in the middle that ties those things together and inform the action based on what is perceived. And as a matter of fact, this is actually so close to robotics that this rough description that you gave or that I just gave, this is also, you know, probably a very good definition of what the hell a robot is, right? So both intelligence in a robot, I think, and what the brain is doing in a human at some level, it's very comparable. And you were saying that the brain solves it very differently. I both agree and disagree because there are actually some surprising parallels, or like maybe it's a projection from the engineers on the brain, right? But we hear a lot about, you know, like feed-forward model, feedback model, control gain adaptation through several and so on. So those, you know, this is like very clear concepts that we use in control theory, for instance. And I understand that they don't translate like one-to-one to the brain, but there are some interesting parallels, I think, or like, you know, to me it's sort of exciting. But again, maybe it's us projecting quite a bit. But I think, and that also goes into like what you're saying, one of the key or like crucial difference is the computational substrate, right? Like the way that the brain counts compared to like how we use computers. where we have continuous numbers and continuous time, whereas here within the brain you have like discrete events and you know, spikes and so on. And that's something that for me, coming from control theory to floating around neuroscience, something that's both exotic and sort of perplexing. And I was wondering, can you say a little bit in terms of like how easy it is to work with this type of computation, with like spike trains and doing work with those type of things, like how well you can use that and translate that into real world sort of like solution and applications?
Sure, I can address many of the aspects you've mentioned. So one aspect you've said is that there are many differences between brains and computers, and there are also many similarities. So let's put the similarities aside. I think we all agree that the overall function is very similar: sensory input processing, building up some understanding, and producing motor output. And maybe, yes, we can find these concepts that have been developed in control theory and other fields. We can also find those or re-find them in brains. There are also fundamental differences, and that's much more exciting to look at, in my view. One of the fundamental differences is that there is distributed computation and distributed storage happening. So in our computers, we typically have some memory area, we have a separate hard disk area, then we have a CPU, we might have a GPU somewhere else. So we have very dedicated processing for typical tasks. There's a memory area, there's a number crunching unit, and so on. In the brain, that's not the case. In the brain, we have these neurons. They are distributed everywhere. The function of a neuron is pretty similar across the brain. Now, many neuroscientists will heavily disagree. Of course, neurons have different morphology, different connectivity, there are differences, absolutely. But in essence, neurons collect incoming information, sum up energy levels, and produce an output signal once they reach a threshold. There's no memory storage anywhere. There is no hard drive in your brain. Whatever your brain remembers is distributed somewhere in this neural activity or in the connectivity pattern. So that's a fundamental difference from how we work with computers, how we design computers, how we operate with computers these days. So that's if we look at neural algorithms, if we try to understand how this consortium of neurons performs behavior, we have to understand how it remembers, how it stores information, and how it produces activity. So that's one of the big differences. We cannot just store some information and retrieve it later. We have to find other ways of handling and memorizing information. Now, the other aspect that Yannick mentioned is event spikes. I've also addressed that a little earlier. So neurons communicate by sending pulses. Now look there's a very popular sensor, an event camera that has been developed over the last 10 years or so, where instead of taking image after image, as normal cameras do, each pixel of this new camera waits for change in its little field of view, in its very small area. And once there is enough change, it sends a spike. So instead of image after image after image, we're getting individual pulses from here, from here, from here, from here, from here, wherever in the image a change happens. This is much more economic. We have significantly lower amount of data. We need lower bandwidth to transmit information, vision information, compared to one image after the other. This is also significantly faster. We have lower latency. We don't have to wait for new images and then wait for the next new image and the next new image, because all these pixels work asynchronously, and as soon as a change happens, the pixel can send out data. So there are some advantages. There are additional advantages. You can read up about event-based vision. There's also a big disadvantage, and that's a real problem, because the data format, the way to represent information, is so different compared to traditional cameras and traditional computer vision. We literally have no idea how to handle that data. We have to rework computer vision algorithms from scratch, from ground up. Whatever has happened in the last 40 years of computer vision, with hundreds of thousands of people worldwide working in computer vision, with artificial neural networks working on images, that does not immediately apply to event-based input. So we really have to rethink how to process, how to handle such event input. And if we do it correctly, if we do it nicely, there's the hope that we develop significantly more efficient algorithms, sparser computation, lower energy needed for computation. So if we look at the whole processing chain from input to output, we believe we can use significantly smaller amounts of computation, lower energy, to get faster overall processing, to have lower latency in that processing. We need to understand how to do that, and we look a lot into real neural networks, into real vision systems that use a lot of biological vision systems that use a lot of neurons to do vision processing, but they do exactly what we would like to do.
And so if you if you think in terms of like both the advantages of this formalism, or like this approach, like this type of technology, and then also the challenges of it, like what makes it hard and so on. Can you talk a little bit in terms of, if you project, in the middle term, or even in the long term, what do you suspect, or like what do you believe will be good or like cool applications of this type of thing? So you talked about like vision. Where can you put the vision? Is this like a surveillance camera? Is it like a camera on a car? Like what is a good application for this, you think?
So in this particular field, if we look at event-based vision and event-based processing, there are a few criteria that needs to be fulfilled so that it's beneficial. For example, we need to have a low power operation. If you have a power outlet in the wall next to you, next to an industry setup, you can probably afford running a GPU card and process in traditional settings. Whereas if you have an autonomous system that has to operate on battery, or this could be a wearable on yourself, or this could be a mobile robot, this could be a surveillance station working on solar power. So if you have to save energy, you have to be crucially aware of your energy, then event-based sensing and event-based processing can be advantageous. So as you said, surveillance, maybe some parking lots, maybe some outdoor area where it's hard to route electricity. If you want to survey in non-human accessible areas, if you want to survey in forests or somewhere outside. Another area is high-speed, low-latency vision, where you need the information right away. So what I mean here is you can easily record with 1,000 frames per second and then process later, and after seconds or minutes, you have a result. That you can do with traditional computer vision. But if you want a closed-loop system that recognizes within milliseconds, within microseconds maybe, what is happening, what is going on in the world, if you need to observe, let's say, a current flowing, some water or something where you have very low time constants before you can react, then event-based vision and event-based processing can be very helpful. So there are a lot of startup companies. There's a lot of interest also from big players in the field in such technology, in both processing for energy saving and in sensing with the benefits. There is some area in autonomous cars where we have to save energy, in electric cars where we have to process quickly because cars drive pretty fast. So all these combinations are interesting in this area of event processing.
I think also, so besides, so when you think in terms of like energy savings, so there's when you are like constrained in terms of like the amount of energy that's available. Also, I think that there can be some considerations in terms of scale. I'm thinking, for instance, of so autonomous driving, but not from the point of view of the vehicle, but of the road infrastructure, right? So people have been, for like the last 4 or 5 years, there's been like large-scale European projects looking into the terms of the type of equipment you want to have on the highways of the future to serve as relays for the onboard intelligence and also to monitor what's happening. And I think, so from what you're saying, I think event-based camera would be like a really good application, because you don't want to spend too much energy like on your sensing. You don't want to sense when there's no cars on the road. Yeah. And also you want to have, millions maybe of cameras if you want to, in the long term, like equip all of relevant roads. And in terms of like moving fast, also I think that probably would be some cool applications if you look at unmanned aerial vehicles, like what people call drones, like maybe quadrotors. Because also the time constant of flying objects is even probably like smaller than driving cars, and they have substantial challenges, in particular when they want to navigate, unstructured and enclosed spaces. Like navigating like a network of sewers, for instance, is one of the applications.
Absolutely. There's a lot of work happening in all these areas. There are some startup companies that work both on the sensors, but also on the processing side. And I mean, there's drone racing as a, let's say, toy example right now, where people spend significant energy in flying through small obstacles at high speeds. And this is all about to be automatized, which then can translate to industry products and everyday electronics in our scenario. One aspect that people have to be aware of is that the algorithm development is really in its infancy. So we are working on finding proper algorithms. And today we're running most of these algorithms on standard computers or GPU cards, or maybe some distributed microcontroller arrays for our convenience. If we really want to make, if we want to take out the benefits of energy efficiency, then we need to go to customized hardware. So there are special chips available that can be designed, that can be built, that will operate only when new spikes arrive, when new spikes come in. So it's dedicated silicon hardware that mimics that brain-style computation, which then will allow us to use these very low power systems in a very low power setting overall.
Can you comment then, like talk a little bit about like the state of maturity of that computing technology then, like how much are people using it, what they're using it for, what's being done in that respect?
There are quite a few companies out that promised that work on general purpose brain-like computing chips. There are fewer companies out that develop individual chips. So once I know this is the algorithm I want to use, I've developed and tuned my algorithm, I understand what my system should do and how it should do that, then I can go into a customized chip for exactly that algorithm. And that's some development effort that needs to be taken. But examples exist. So there are projects for hearing aids, there are projects for surveillance, for observation, for counting, similar aspects. So initial projects exist where companies have demonstrated that such systems can be built in the very low power domain. So there's no general purpose block out there right now that offers low energy, but overall we can demonstrate that this works, and this is very promising for the future.
Because specifically, so not necessarily like reprogrammable, but like custom built, like to reflect then the algorithm. Okay, cool. That's
exactly.
really cool. That's really exciting.
So I think we're close to out of time. Yannick, this was a pleasure talking to you today. I think we've covered quite an area, quite a wide field of topics that we work on. It's a bit on one outside area of HPP, but it's important. I think it's a very important and very valuable path to take results from brain-inspired computing into applications into industry. Yannick, anything else for you?
No, I agree with. So thanks for taking the time to hang out and enjoy the conversation. I agree with you with the merit of this perspective, and I think there's a lot of still untapped potential. Of course, there's a lot of like very exciting topics and problems that are coming up all the time. It's a very fertile field to explore, and very, very exciting.
Very good. I think that's all from us. Thank you. Yannick, it was a pleasure talking to you. Thank you to all the audience for joining us for this discussion today. If you're interested, if you would like to learn more about this research, then please, you can visit the Human Brain Project website. The address is www.humanbrainproject.eu. And now I wish you a very great afternoon. Thank you and goodbye.